We can use the curl and divergence and rewrite the Green's theorem. So take a look at the following. Suppose F is a vector field with components P and Q. Remember that the line integral is defined as F dot dr over smooth curve like C, which is defined as P dx plus Q dy. And then remember that we defined the curl of F as follows. Curl of F is defined as I, J, and K, partial derivative with respect to X, partial derivative with respect to Y, partial derivative with respect to Z of the components that you have P, Q, and the last component is just 0. So you have I with 0 and taking the partial derivative of Q with respect to Z. This guy is also 0. Why is that? These two functions are in X and Y. So far we have a 0. Minus J, well, here you have partial derivative 0, and here partial derivative of P with respect to Z. This is going to be 0 again because it's in X and Y. Plus K, and here you have partial derivative of Q with respect to X minus partial derivative of P with respect to Y. So far we have curl of F defined this way. So curl of F dot K, remember K was defined as vector 0, 0, 1. It gives us 0, 0, and partial derivative of Q with respect to X minus partial derivative of P with respect to Y, dot product 0, 0, 1, which gives us the last component, partial derivative of Q with respect to X minus partial derivative of P with respect to Y. So curl of F dot K gives us the difference between the partial derivatives. So Green's theorem can be written this way. Here you have the line integral of F dot dr over curl C, which is equal to the double integral over region D, which is bounded by C. Now you have partial derivative of Q with respect to X minus partial derivative of P with respect to Y, which is curl of F dot K. So just replace that. Curl of F dot K dA. So converting the Green's theorem using curl. Another important note for you. I'm going to write this down a little bit further here. I need a little bit of more space. So Green's theorem using curve. We have the line integral. Move it here further down so I have enough space. We get the integral, line integral of F dr over c, which is equal to the double integral curl of f dot k dA. Okay, so now let C be given by the vector equation as follows. Suppose RT is equal to x of t and y of t, and t is bounded between a and b. Recall that the tangent vector t is equal to, let's make it as a unit tangent vector. Unit tangent vector t is equal to, here we have x prime of t divided by the length of our r prime and y prime of t divided by the length of r prime. Using the unit tangent vector, we can create the outward unit normal vector. These are the things that you learned in elementary calculus. Outward unit normal vector n of t, which is, well, equal to y prime of t divided by the magnitude of r prime and x prime of t divided by the magnitude of r prime. Very good. And it has a negative sign as well. Don't forget to put the negative sign. So in that case, if you write it this way, then you can convert your line integral as follows. The line integral of f dot n ds over curl c is equal to the integral a to b. Here you have f dot n, a variable t, so let's just write variable t down here to avoid any confusion, times the length of r prime dt. Okay. Very good. By using our computations here, if we substitute them over here, what do we get? We get the integral a to b of p y prime divided by the magnitude of r prime minus q x prime up here, q x prime divided by the magnitude of r prime times the magnitude of r prime dt. We can simplify this. We can get rid of r prime of t, the magnitude, and as you can see, you get your line integral simplified. Okay, do we have enough space? Maybe just a little bit here. A to b of p y prime minus q x prime dt, which is equal to the integral p dy minus q dx over c, which can be written as double integral. Let me move the board a little bit here. Can be written as the double integral over region D, partial derivative of p with respect to x plus partial derivative of q with respect to y dA. So the second formula is the line integral f dot n ds is equal to the double integral of divergence of f dA over region D. So we derived two important formulas connecting the line integral to the curve and also to divergence. So let us summarize what we learned. Circulation curl and outward flux divergence. Flux divergence. So for the flux divergence, if you have a vector field F written as P, Q, M, and N, if you open different calculus books, you might see different components. In that case, the line integral over curl C, F dot N ds is equal to the line integral P dy minus Q dx, which can be written as the double integral partial derivative of P with respect to x plus partial derivative of Q with respect to y dA over region D. So this is your flux divergence, and for the circulation curve, the same process. If vector field F is given to you as P and Q, then the line integral of F dot T ds over curl C can be written as the line integral of P dx plus Q dy, which is equal to the double integral partial derivative of Q with respect to x minus partial derivative of P with respect to y dA over region T. But let's take a look at a couple of examples. This example says, find the outward flux of the vector field F, which is defined to us as x, y squared, across the square bounded by the lines x equals to plus minus 1, y equals to plus minus 1. So our goal is to calculate the flux. Let's follow the formula. The flux is defined as the line integral f dot n ds for the line integral p dy minus q dx, which is equal to, well, as you can see, the double integral partial derivative of p with respect to x plus partial derivative of q with respect to y dA over region D. Now the calculation is not that hard. Here you have the boundaries for your x, you have the boundaries for your y, they are fixed. So this double integral, -1 to 1, -1 to 1, 1 plus 2y. You can take the integral with respect to y or with respect to x, it doesn't matter. Here you have, for example, dx dy, which becomes integral -1 to 1. Here you have 1 plus 2y dy, and Fubini's theorem says, hey, you're allowed to separate these. So this becomes y plus y squared, -1 to 1, multiplied by x, ranges between -1 to 1. So here you have 1 plus 1 minus -1 plus 1, this is just 0, multiplied by 2. So the output value is 4. The flux is 4.